this video, we're going to talk about polynomials, factoring the sum and difference of cubes. This is more of an advanced topic in factoring, at least one of the more advanced topics in factoring that you'll find in an algebra textbook. And often it's held off until later on in a course for one reason or another. I'm not entirely sure. However, we're going to just go ahead and introduce the idea of how to factor the sum and difference of cubes here. And as a preview, just to show you kind of what's upcoming, first thing we're going to do is prove the sum and difference of cubes factorization formulas. We'll probably just prove one of them. The other one will be just as easily done by you. And then we're going to do some factorization examples. There are two real prerequisite keys to success for this lecture. The first one would be that you have to be very familiar with polynomial multiplication. That's just required for the proof, but also you have to pretty much understand that polynomial multiplication is the inverse of polynomial factorization. So factoring is like dividing, and then distribution is multiplying. The other key to success is that you have to understand how to factorize. Not that you're going to necessarily need to know the sum and difference of cubes formula right away, but you have to understand what factorization really means. If you don't know either of these prerequisites, you should go back and review some of the previous lectures I've done on polynomial multiplication or factorizations. Now, in order to introduce the idea of this factoring the sum and difference of cubes, I'm actually going to start off with cubing something first, and we're going to discover kind of what this cube turns into, and then we'll learn a little bit more about multiplying two special polynomials together. But first, let's start with this. Whenever you have an object raised to a power, you know that means that that object, which in this case is x minus y, is being multiplied by itself that many times. So we have x minus y quantity being cubed means that we have x minus y times x minus y times another x minus y. And if you have this many objects multiplying, you should take it two at a time. In other words, take one of these binomials, x minus y, maybe the first one if you want, and multiply it by the second binomial or any of the other binomials. I'm just going to choose the first and the second here. So that's a process of distribution. Just remember that you're going to get some answer or some product, and you still have this x minus y hanging off in the back here. So just remember, when you multiply these first two binomials together, they have to be in parentheses. When you do that, you get an x squared minus an xy minus another xy, so that would be a minus 2xy. And then finally, plus y squared. And now we'll go ahead and multiply these two polynomials together. You have a trinomial times a binomial. And remember how this multiplication works. You do a distribution. X squared gets distributed to each of these objects in the second factor here. And then a negative 2xy also gets distributed over there. And finally, the y squared itself will also be distributed to each of these terms. I'm just showing the action right here. So let's go ahead and do this multiplication. X squared times x will be an x cubed. X squared times a negative y will be a negative x squared y. Now we have a negative 2xy times x will be a negative 2x squared y. A negative 2xy times a negative y is a positive 2xy squared. Finally, we have a positive y squared times a positive x, so that will be a positive xy squared. And we have a positive y squared times a negative y, which will be a negative y cubed. And our goal here is to combine like terms, so let's go ahead and do that. I don't have any other x cubes other than the first one. And as far as x squared y's, I have a negative 1 of them here, and I have a negative 2 of them there. So altogether I have a negative 3 of those x squared y's. And now as far as the xy squareds, Well, I have two of them here, and I have another one of them here, so altogether I have three of them. Let me write that in, a positive 3 of those x squared y's, and finally a negative y cubed. Nothing else really combines. And that's kind of an important point to make, is that there are no other like terms here. The next example I'm going to do will show you that sometimes things will combine so much that you lose almost all the terms and you just compress down to a couple terms. Now in this example, I'm just asking to multiply this binomial times this trinomial. I'll do the same action that I did a moment ago, where I just went ahead and distributed this x to each of the terms in the trinomial, and I'll distribute the negative y to each of the terms in that trinomial as well. Let me just get that going over there. Okay, when I do that, I get the following. This is going to equal, let's see, an x times an x squared is an x cubed. Okay, an x times a positive xy is a positive x squared y. And finally, an x times a y squared is a positive xy squared. And actually, I should have written these in red, because that's what I was doing with that action there. Those are all the red actions. Next one I'll write in blue, just to kind of delineate the two. A negative y times an x squared is going to be a negative x squared y. A negative y times an xy is going to be a negative xy squared. And finally, a negative y times y squared is a negative y cubed. We're going to go ahead and combine like terms, and you see that I don't have any other x cubes other than the first, so this is just going to equal x cubed. The second term is an x squared y. Let's see if I have any other x squared y's. I do. One right there. So I have a positive one of them, and I'm losing one of them. So they cancel out. So I don't have to worry about those. And then the xy squareds, well, let's see, I have a positive one of them there, but I am losing one of them here. So again, those two cancel out. The only other thing I have left really is a negative y cubed. And this is a very interesting result, that you have the product of this binomial and this trinomial that compresses down to x cubed minus y cubed. And this brings up a very important theorem. The sum and difference of cubes theorem states the following, that if you have an object being cubed plus another object being cubed, in this case I have a f as the first object and an l as the last object, it will factor actually to the first object plus the last object times the first object squared minus first times last plus last cubed. Now the format of both of these theorems here that you see, one's the sum of cubes and one's the difference of cubes, is exactly the same except for some sign issues. The easiest way to remember this, though, is that if you have a sum of two objects being cubed, well, the first part of the factorization is a sum, first plus last. If you have a difference of cubes, first cubed minus last cubed, then the first factor will be a difference, first minus last. So basically, you keep the sign initially. The second factor is always first cubed, and then there's either a plus or a minus, first times last plus last cubed. It's just that sign that's in between the first cubed and the first last terms is always the opposite of what you are actually interested in doing. So if you're dealing with the sum of cubes, that would be a minus sign there. If you're dealing with the difference of cubes, it would be a plus sign. This is one of those formulas, one of those theorems that's actually much easier for students to memorize than it is to prove every single time. There are a lot of theorems in mathematics that are easily proven if you happen to forget the exact form, but you kind of know what's going on. But this is one of those that's very difficult if you don't know the exact factorization or have no clue how it factors. It's very difficult to know this without memorization. So I'm going to just encourage you in this very rare case to memorize this, but also spend some time looking at the last example that we did, which was to kind of prove the difference of cubes formula. This is actually the proof of it. we basically said, oh, if I have x minus y times x squared plus xy plus y squared, it will become x cubed minus y cubed. Or in other words, x cubed minus y cubed is equal to the product of those two polynomials. So let's go into a couple of examples. We don't need very many for this concept, but it's good to kind of go through a couple at least. So let's look at factoring 27a cubed plus 64b cubed. First thing you should ask yourself is how many terms do you have in this polynomial? If you're being asked to factor, you should always ask yourself how many terms there are. We have 2 here. So that tells me that this is likely either a sum of squares or a sum of cubes because we have 2 terms and there's a plus sign. So I'm hoping it's going to be a sum of cubes because I see third powers here. Now again, you always look for, and maybe I should write this along the side here, and this is a very truncated instruction set. If you want the full instruction set, you should go back to my factoring videos. But this is basically saying that you always look to factor out the greatest common factor first. So you're looking at these 2 terms and seeing if they share anything in common, which they do not, so don't bother with that. And then you go ahead and start seeing what kind of factorization it would be. I generally like to write it, if I think it's a sum of cubes or a difference of cubes, I'll write blank being cubed plus blank being cubed, and I'll fill in that blank. Because it's just a better way to kind of do this style of factorization. So what number, when it gets cubed, becomes 27? Well, that would be 3. So 3 cubed is 27. What variable, when it gets cubed, becomes a cubed? Well, a. A being cubed becomes a cubed. And the same thing over here with 64. That's actually 4 cubed, and then we have the b being cubed. So in terms of our theorem back here, what's playing the role of first and last is, and I had to adjust something there to kind of make this look a little bit better. But anyway, what's playing the role of first in this case would be 3a. So that's our first object being cubed. And what's playing the role of L, the last object would be 4b. So remember how this factors. This is going to be the first object plus the last object. And actually, let me write this in green. So it's the first object, which we know is 3a, plus the last object, which we know is 4b. This is how I generally start this factorization. I know it's going to be the first thing plus the last thing. And then I forget about looking at this problem, anything written prior to this, from this point forward. I only concentrate on viewing 3a and 4b. I only look here. It's a huge mistake students make. They start looking back at this 27, this 64, this cubing process. They look at all the stuff except for what's important. What's important here is that you have a 3a and a 4b. 3a being first, 4b being last. So let's go ahead and finish out the factorization. I know it's going to be this first object here squared. So that's 9a squared. I also know that because this is a plus in between the 3a and the 4b, there's going to be a minus here. It's always the opposite sign. And then I'm just going to multiply 3a times 4b. So that's going to be 12ab. And then finally, this is always a plus back here, plus that last object being squared. In other words, that 4b, this object right here, being squared. So we get a 16b squared. And that's it. That's all you can do. There's no other way to factor this down any further. If you already factored out the greatest common factor, then this will not factor any further. This trinomial on the back end will be a prime polynomial, so it won't be factorable at all. So that's it. That's how you would factor a sum of cubes like that. As a second example, let's go ahead and take a look at 125a cubed b to the sixth minus 1. Again, I'm going to first look for a greatest common factor here, see if both these terms share something in common. They do not, so I don't worry about factoring anything out. And then I think about this. is this a, well, first of all, is it a sum of two objects? No, it's not. It's a difference of two objects. And also, the fact that it only has two objects means the only way that this can possibly factor is if it's a difference of squares or a difference of cubes. And actually, something I want to mention about something I did a moment ago. In this previous example back here, I had mentioned that because we have only two terms here, you really only have a couple options. Either it's a sum of cubes or a sum of squares. But you should have recognized at that point there's no such thing as a factorization for a sum of squares. So really, if you have a sum and you see two cubes in it, then you know the only way, or actually basically if you have a sum of two objects, the only way it's going to factor is if it's a sum of two cubes. Okay? So there's no way you can factor a sum of two squares. However, when you have a difference of two objects, well, there is a difference of squares formula and a difference of cubes formula. So in this case, we have a couple options that we might be able to exercise. But you have to ask yourself, is 125 any number that you know squared? That's not a perfect square. So this is not going to be a difference of squares here. It's actually likely to be a difference of cubes. If it is, and hopefully it is, I'm going to go ahead and write it as something cubed minus something else cubed. The easy one here is to notice that 1 is the same thing as 1 cubed. So that last, in our first minus last formula, in our first cubed minus last cubed formula, the last object is 1. But the first object here, well, let's see, 125 is the same thing as 5 cubed. A cubed is the same thing as A being cubed. And b to the 6th power is the same thing as b squared being cubed. So in this case, our first object is 5ab squared. Let's go ahead and see how that factorization works. Recall from our theorem back here, I'll just pop back here real quickly. The difference of cubes formula says that if we have a first object being cubed minus last object being cubed, it'll factor into first minus last times first squared plus first last plus last squared. So let's go ahead and try that out. And just put in some parentheses here because I know I'm going to have a small binomial there and a large trinomial at the end. The first object was 5ab squared. And then we have a minus sign. We have to match up these signs. And then the last object was 1. And from that point forward, I forget about all the other numbers before this and I just concentrate on a 5ab squared and a 1. Okay. Let's see here. I know that in the trinomial here, it'll be the first object, which is 5ab squared, being squared. So that's going to be a 25 a being squared, b squared being squared, which is the same thing as b to the 4th. Then I know the sign in between this term and the next one. It's going to be the opposite of that minus sign, so it's going to be a plus sign. And now I'm just going to multiply these two highlighted, the first and last term. So 5ab squared times 1, or in other words, 5ab squared. And finally, it's always plus, and then the last object being squared is 1 times 1, or in other words, just 1. So 125a cubed b to the 6th minus 1 factors to 5ab squared minus 1 times 25 a squared b to the 4th plus 5ab squared plus 1. And you should be able to get the idea from this point forward how this theorem kind of works. And like I said, it's more of a memorizable theorem. I think that you have to commit this one to memory to be able to use it properly.